In this 6-minute summary video, we're going to take a look at what are called higher dimensional models. We'll talk about decision boundaries, and then we'll talk about something called k-fold cross-validation. So we have for a long time been using a scoring function that was very simple in order to get a good visual of our data. So we've been using two different features, V1 and V2, so that we can have axes here and here. And then we've had three features, really. We have this constant term, the coefficient on V1 and the coefficient on V2 to represent our scoring functions. And what we're going to do first is talk about what happens if, well, what if we wanted to consider not just these two features, V1 and V2, but maybe we want a model that takes into account that scoring function, but also takes into account the square of those terms and maybe a cross term here, the way that these two features relate to one another. And so what I'd like us to do is see how that helps us visualize what's called the decision boundary of our scoring function. So recall when we started with the bag of words model, that model was really indecisive. For example, that model would get a score of 0 quite frequently, and when it received a score of 0, that meant that the probability was 50% of the review being good or bad, and in essence, the scoring function couldn't make a decision about that review. So a decision boundary is the collection of points where the scoring function would give us a 0 and be indecisive about the model. And what that decision boundary is going to do is cut our data into two different sections, part that's above the decision boundary and part that's below the decision boundary, where it's going to group everything above the decision boundary as one type of review and everything below it as something else. So for example, if I return to that original scoring function, s1 of x, it draws a line through our data, and that line is going to separate positive reviews from negative reviews. And so you'll see this line, everything below it is deemed a positive review, and it would deem everything above it a negative review. And I've kept the original coloring on our data in order to see how accurate that model is. Now, there's a little bit of overlap between our data. Some of these points have both positive and negative reviews present for it. If I switch to the scoring function S2, you can see that what I get is a quadratic for my decision boundary. And what would be happening here is that I would be viewing everything above the quadratic as a negative review and everything below the quadratic as a positive review. And so it's splitting my data in this different way. So one of the benefits of using higher order models is that we allow the decision boundary to bend a little bit to accommodate the fact that not all things are classified in a straight line manner. Now, just with everything else, and what will lead us into our second topic is, it's very possible to overfit by repeating this process, by looking at cubics, 4th degrees, 5th degrees, etc. If you allow your model to go too high and you get something that starts to perfectly zigzag around everything just so to make it perfect, remember that you're drawing these decision boundaries based on your training data, and when you start to have utter perfection in the division of positive and negative reviews, you most likely have an example of a function that's been overfit. And so we need to be able to do some testing on these various models in order to determine if we have a good fit or something that's been overfit. So this leads us to think about something called k-fold cross-validation. So the old story is we begin experimenting with a huge amount of data where we know everything. And we liked to use a good portion of that data as training data to create a good model. And then we want to evaluate that model on data it's never ever seen before. So we would set aside something like 20% of our data be totally unseen and untouched by the training mechanisms, so it could be a fair, unbiased judge of how good the model is. If we start having degree 1, degree 2, degree 3, degree n polynomials, and we want to know which one is the best one in order to make decisions, if we're then going to repeatedly tweak different parameters of our model, it's not really good data processing to use the test data to both tweak the model and then assess its performance. As soon as the model sees the test data and we make decisions about the model based on how it did there, it's no longer unbiased data. So one solution is to take the test data and split it in half, say, into what we called a validation set. This became particularly problematic with logistic regression because very frequently we're dealing with data that is not split evenly in its categorization. So we start to get these smaller sets of data that don't really have a lot of examples of one type of behavior, and we just don't know how reliable an assessment is coming from that very small data set with very few examples of the behavior that we're looking for. And so to solve this, we turned to what was called k-fold cross-validation, where there was a beautiful animation of this. Now in k-fold cross-validation, what we're going to do is break up our data, our training data, into these 4 different sections. And what we'll do is use the first 3 sections to be our training data and the last section to be our testing data. And we'll build a model that way and come up with an error that way. Then, in order to get a different perspective, we'll change things up. Maybe we'll take that first section and make the first section the new testing set, and the last 3 sections will be our training data. And so we'll build this model on the 3 sections and reserve one of the sections to be unseen when we create the model to be our testing set. We'll repeat that with all the different sections. And what we'll do in the end is have, in this case, 4 different models, 4 different test sets, and 4 different error measures. And we can take the average of those error measures to see on a whole how well that model does. And one of the big benefits of this method is that it lets us get a little bit of diversity in our testing samples so that we see the full set of possible outcomes, even if each particular test set is small. So this is k-fold cross-validation, very powerful technique, something that we should be seeing again in the future.